रिकॉर्डिंग स्टार्ट करिए रोहित जी, और ज्योति जी आप प्रोसीड करिए.
Okay, sir. Hello and a very good evening to one and all present here. I again welcome you all to the 1-month international training cum certificate course on precision agriculture, farming with new perspective. So today we have with us Dr. Manjeet Singh, working as Assistant Principal Scientist in Department of Farm Machinery and Power Engineering at Punjab Agriculture University, Ludhiana. Talking of the educational career of Sir has done his B Engineering from Rajasthan Agriculture University and MTech and PhD from Punjab Agriculture University itself. Sir is working as principal scientist and has joined the department as assistant professor of agriculture engineering in the year 1996. So talking of the profile of Sir is a dynamic professional with 26 years of experience in project management, research and development in agriculture machinery, coordination, technology, transfer and team management. Under his guidance, there have been a development of 30 machines as well as the technologies, and he has been recommended 23 machine and technologies. He has different patents under his head and has published more than 274 research papers which were published in national and international reputed journals. Sir is extensively on visit to different countries for providing the technologies to the different countries. So here we have with us Dr. Manjeet Singh, sir. So he will be elaborating today to all the participants regarding how precision agriculture would be helpful in farm machinery or in agriculture. So I welcome you, sir, for the today's lecture.
Thank you, Madam Jyoti Sharma, for the nice introduction. So, can I share my screen?
हाँ बिल्कुल सर, बिल्कुल.
Is it okay? It's visible?
Yes, sir, it's quite visible.
जी डॉक्टर साहब बढ़िया तरीके से दिख रही है.
Okay. So, thank you, Dr. Ankur Sharma and Madam Jyoti Sharma, for inviting me. So for this presentation, topic given to me is generation of georeferenced yield maps. That's the basis of precision agriculture or precision farming. So as Madam told, I'm working as principal scientist in the Department of Farm Machinery and Power Engineering at Punjab Agriculture University, Ludhiana. So this presentation will basically is divided in 3 parts. As first will be the introduction about the topic or introduction about the precision agriculture. There might be some repetition in this because you are in this course from, I think, few days ago. So this course has been started and now some parts may be repetitive, but I will try to link this with the precision farming with the yield monitoring system or yield maps, and then how it can be measured or how this maps can be generated. So that will be second part of my topic. And then third, conclusion, or what are the other types of data that can be correlated with this yield to start this precision agriculture. So my first slide is that how this evolution of agriculture has been done. So earlier there was that animate farming. So in this animate farming, there was low input and low output. So more human and animal force or animal power or human power. So, but there was no or lesser intelligence was required for that type of farming. Only these animals or bullocks or camels or these were used for the farming. So then slowly we shifted to mechanized farming. So in this mechanized farming, there is high input and high output. So this more mechanical force was required for the tillage, for the other operations of the agriculture. And definitely this human intelligence was also involved or is also involved in this mechanized farming. As farmer or driver or operator of these machines are also involved in this. So this is mechanized farming. And now we are slowly shifting towards this digital or precision farming. So in this, there is optimized input and output. So this mechanical force is there with human and artificial intelligence. So this is in nutshell that how we have shifted from this animate farming to digital or precision farming. So this is complete agriculture system. As you know that we are giving inputs, seed and soil and water and this fertilizer, chemicals, labor, and then machinery also. Machinery in terms of power as well as machines. So these are the inputs which we are providing in our agriculture system. And we are getting outputs in terms of yield, quality and environment. But I have put question mark for the quality as well as for the environment. So question mark, why question mark? Because our farmers or we as a scientist are also more bothered for the yield and lesser for the quality as well as environment. But now we have to consider, or in future, there is need to consider for the quality as well as environment along with yield. So yield is important, but quality and environment are also important for the as the output for the agriculture system. This because I belongs from this mechanization discipline. So I am starting this my presentation or my this next slide is about mechanization index or farm power availability. So how this is measured? So this is measured that how much power is available per unit area or per hectare or per acre. So this is the index, or this is the you can say formula that how this mechanization index of any farm is measured. So if we talk about some countries in this, so this USA is this is little bit older data. So this is just for a comparison that where we stand and where other countries are doing in this area. So in this, as USA is using 6 kilowatt per hectare. In Japan, this is 14 kilowatt per hectare. Korea 7, then Germany 2.4, France 2.6, and India is using only 1.4 kilowatt per hectare. So this is as we are far behind from these all these advanced countries as far as this mechanization index or farm power availability is concerned. So this is overall scenario of India as because that was a little bit older data. So now we are using power at the rate of 2.76 kilowatt per hectare on an average in India. But if we talk about Punjab, so which is at the highest level, so Punjab is using 4.92 kilowatt per hectare. So that is 80% more than the India average. So this how this is calculated, or how what are the sources of the power which are involved in this calculation? So as a major part is tractor power. So this is in India now 60% of the share of this tractor power. Then power tiller 1% only, diesel engine 14%. Then electric motor, that is about 20%, and then animal, still we are using, or some states are using animal power as a source of this farm power. So 3%, and human power is also calculated in this index. So that is also about 3%. So this is the how this in India we are using this farm power at our farms. So this is directly correlated with the food production, as you can see in the graph. that when this farm power or this mechanization index is increased from 1961-62 to 2020-21. So in the same rate, this food production or productivity, you can say food productivity has been increased in terms of ton per hectare. And similarly, if we talk about India, so in India, this is because this Punjab is using 80% more power. So similarly, this food production in Punjab is also, you can say, more than this 80% or double that. That is the average of the India. So this is how this mechanization index is directly correlated with the productivity. So why now we use or we need this advanced farming or precision farming or digital farming? So there are many terms in India. So because there are some 4 or 5 reasons which I want to discuss with you, that this first major reason is blanket and uneven application of inputs, like for example NPK, which is required only 4:2:1, but we are using in the ratio of 18:6:1. Then second reason is that depletion of water resources. Continuously we are pumping water out of this ground. So this is due to that there is depletion of water resources, even as Punjab was considered that there is a lot of water. So now we are also facing this issue of depletion of water. So this is also a serious problem. And then more environmental pollution due to chemicals and due to burning of straw. This is also we are facing in a big way in northern part of the country, as far as chemicals are used, as well as burning of straw, especially this rice straw, because wheat straw is used as an animal fodder, but this rice straw is not used as animal fodder. So this is burnt by the farmers. So then next reason is that we have low productivity of crops, as 30 to 50% below the international averages, and then high growth of population. So this population is increasing faster than its ability to produce rice and wheat. Then very high post-harvest losses. So that is in the range of 25 to 30%. Then 10% of produce is only processed in the country, as against 40 to 60% in other South Asian countries. I'm not talking of advanced countries, but South Asian countries. They are processing their products or their agriculture produce is in this 40 to 60%. We are only processing 10%. And then nutritional insecurity in rural population. So this is also a issue in our case or in our Indian conditions. So these are some reasons due to which we need this precision farming or advanced farming at our farms also. So this is data. Data is very important. So when we want to manage anything, so we have to collect the data or measure. If we measure something, then we have to manage that. So this is the basis of precision farming. So data is required. So measurement will give data. If we measure something, so there will be data only. So that this will be a commodity like oil and gold. So in future, this data will be a commodity like oil and gold. So what we can extract from data? So this analysis of data will give some information or knowledge. And then from this knowledge will provide some intelligence. And finally, when we add economics and or other parameters of this, then that will lead towards wisdom, or you can say final management of the farm, that how we can manage our farm. So this is a Japanese philosophy, that how data is to be converted into wisdom. So now we can discuss that what is precision agriculture. There are two this most popular definition of this precision agriculture. So in nutshell, this is better input management. So what are the inputs we have discussed already? So if we manage or optimize those inputs. So that is basically precision agriculture. So this is given by five. Earlier this was 5 hours. Now one more hour has been added in this. So what are those 5 hours? So first is right input. So when we want to select any input for our farm, so that should be right, as I have given one example of one chemical ulala, which is used for the control of whitefly in the cotton crop. So then if first we selected this right input, then amount or dose of that input which we have selected, that should be right. For example, for the ulala, this should be applied at the rate of 80 gram per acre. So then this is third R is right time. So when we have to apply or when we have to use that input. So that as example is given for this whitefly. So above ETL or 6 to 8 numbers of that whitefly per leaf, then we have to apply, or that is the right time to apply that input. So this is third R, and fourth R is right place. So where we have to apply. So in this, as in case of whitefly, this resides in the middle of canopy and underside of leaves. So that is the right place. So this is where engineering people or we people plays a role in this as right place and right manner. So right manner means kaise apply kaise karna hai. So that is which type of nozzles are used. So as drop-up nozzles, we designed these drop-up nozzles especially for the control of whitefly. So this is how these 5 R's are explained in this precision agriculture. And now another 6 R has been added, that is right genetics. So this is also when material or that variety of that crop or seed is not right, then what is the use of these 5 inputs, or better use of inputs, or better input management. So this 1 R is recently added in this. So this philosophy is basically better input management. So this is one definition. And then another definition in this is that whether this precision agriculture is a new technology. So my viewpoint is no, because this is basically input management philosophy to respond for variability. So this is the basis of, you can say, precision agriculture. When there is variability, so there is a need of precision agriculture. So this variability may be in soil, or maybe in plant, or maybe in yield or quality. So what are the parameters which are playing important role in agriculture? If there is variability, so then there is need of precision agriculture. So this is this variability is also measured at 2 level, or at 2 you can say 2 way. So one is spatial variability and another is temporal variability. So spatial variability, I think you know that with the space or with the location of as we generally take GPS data for this. So this is variation at the spatial level, and temporal means with the time, that with the time of maybe last year we take yield data, and this year we take yield data, and maybe next year we take yield data for the same field. And then we can get some idea, or we can conclude that where in my field there is variability, or there is change in the yield, or same yield, or change in yield, whatever the variation. So that is at the with the time scale. So it means this this data is taken at spatial level as well as temporal level. So this is by using advanced technologies. So this is not a new technology, precision agriculture, but this is the use of new technologies or advanced technologies like hydraulics, pneumatic, laser, static electricity, electronics, sensor, camera, space, remote sensing, satellites, all these stuff, which is now you are, I think, learning from last few days. So all the use of these advanced technologies, and to make it possible or make this agriculture. So that is basically precision agriculture. So now we will come to yield monitoring system. So which is the our main topic to discuss. So this is the basis of precision agriculture, because this is the major output of that agriculture system, which we have already discussed, and we are mainly concentrating on this yield part. So if there is variability in the yield, so then this variability is basically outcome of that, how we have managed that our farm. So that is the outcome of that our management which we have done on the farm. So that comes for the that will be reflected in the yield data. So this yield monitoring is the basis of precision farming, so which allows farmers to assess the yield variability within the field during crop harvesting. And as we have discussed, that this is the first step to start this precision agriculture. So these are some other importance of this yield monitoring to measure the yield variability within the field during the harvesting. So this helps farmers for an exact assessment of their crop production. It provides tools to researchers for performing experiments and then making strategies and planning to manage yield variability. And it also helps in decision makers to implement the food policies and price regulation. So this is some other you can say advantage or importance of this yield monitoring. So this is this you can say functions of this yield monitor. So this data from the monitor and GPS system used to create the yield maps for each grid in the field. As word is georeference. So in my topic, that word is georeference. Georeference means that if we take yield data along with the GPS data, so that is used to create that yield maps for each grid in the field. So that is basically georeference yield maps. So this is by mounting in combine harvester charges for custom hiring charged by the operators on the weight basis. So nowadays, when these combines are used mainly on the custom hiring basis, so this operators charge from the farmers on the acreage base or on the area harvested basis. So that is not exactly a right way. Right way is that how much yield has been or how much grain has been harvested by the combine. So on the basis of that custom hiring charges should be fixed. So if we will get that yield monitoring data or yield monitoring system on the combine, so then this charging by the custom hiring operators can be done from the farmers. So this is another advantage of this GPS yield monitor data or yield. So this is because in advanced countries, in USA or in Australia or in Canada or in UK, so all these combines are fitted with the yield monitoring system. So they are already fitted, and also this comes as an optional attachment if any farmers want to use that. So that can be used by the farmers. Custom hiring operator gives that data to the farmers. So, but in India, we don't have this, but we started working. We were having one project under NAIP in our university. So we started working on this yield monitoring system. So we come to know that the world over, these two types of yield monitoring systems are fitted on the combine harvester. One is batch type, another is continuous type. So in batch type, there is independent single unit, then combine mounted or trailer mounted, and this continuous type, mass or impact type or volumetric type. So mainly in the advanced countries, this mass or impact type or volumetric type are used. But these batch types are very simple and very, you can say, not very complex. So this, we started to develop this batch type yield monitoring system. And then we also shifted towards this continuous type. So this was our first very, very simple system, batch type, independent single unit yield monitoring system. So as you see that there is load cell fitted at the bottom of this tank, which is blue one, that tank. When combine is to be emptied or the grains from the tank of the combine is to be is to be removed. So then those grains are put into this system or this tank, which is having load cell at the bottom of this, so that we can know that how much, let us suppose that this combine has harvested 2 canals or 1,000 meter square area. So then this will be unfilled to this tank, so that to know that how much is the mass of that grains. So very simple device, but this, because it was reducing field capacity of the combine as well as laborers, more number of this laborers or labor requirement is used in this. So then we this system we tried that we put it in the trailer, and then same operation of emptying that grain tank to this trailer, so that there should be lesser power or labor is required to get again put into the trailer. So this is very simple device. But then finally not finally, in the midway, we were not you can say satisfied with that solution. So what we have done, third this attempt, this auxiliary tank was installed in the combine harvester main tank. एक छोटा tank हमने वहां लगा दिया, तो 500-600 kilograms of that grains can be put in this auxiliary tank, and at the bottom of this grain tank there was a load cell, and then display unit was in front of the driver. So continuously these grains were coming in this tank, and then this data was coming in front of the driver. But again, issue in this was that because this was smaller tank or 500-600 capacity of this tank, so then again we have to stop the combine, then we have to again empty it and put in the main tank. So again there was labor was required for this. So this is how you can say that some pictorial view of that. That smaller tank is put in the main tank, and at the bottom is there is load cell. And then we also put one sensor on the tire of the near the tire of the combine, so that we can get this area harvested also. So area harvested was coming, and then this weight was coming. So in that way, this was yield monitoring was done by using this type of system. This is some dimension of that. Size of this tank was this, capacity of 200 kg for rice and 400 kg of wheat, fitted in the main tank of combined. Load cell capacity was 500 kg. So in this is these are the some you can say specifications of this system. So then finally we developed this continuous type. So that is measures and records following information. Grain flow was measured, moisture was also measured, because moisture is also an important data during the harvesting of any crop, and then area covered, and then location by the GPS. So these are some you can say components of this yield monitoring system, this continuous type. This is having moisture sensor, then this GPS is there, field computer is there, optical sensor. So these are some parts of this yield monitoring system. And this was installed as you can see that there is an elevator which is taking grains to the tank. In that elevator, we fitted that optical sensor to measure the height of the grains in each pedal. And then this is where this you can see that this yield sensor was installed in the combine elevator. So this is how mounting of the sensor was done. This is another view of that. This grains are basically moving from bottom to the grain tank. So in that elevator we put that sensor, and GPS was also there. This was giving area harvested and location. Moisture sensor was there, optical sensor was there. So these are the parts of this yield monitoring system. So this is basically the sensor was measuring as you can see in this diagram, that height of pile of grain on each pedal in grain elevator is measured with that light beam. So sensor was basically, they were cutting when there was in between these beam of these sensors. So this was recorded, that how much time this beam is cut by that. So that is basically directly related with the height of the grains. So this height was then multiplied with the speed of the elevator, and then area of that the lugs or that buckets. So then this gives volume flow, and mass flow is basically calculated by volume flow into grain density. So this was the formulas used to calculate the mass flow. This is now fitted with the GPS. You can see that GPS is at the top of the combine, and this was the you can say more closer view of this GPS. And then moisture sensor, this was fitted at the bottom of that grain elevator. You can see that this is where this moisture sensor was fitted, and this moisture sensor was basically principle of working was this was the capacitance based. So this is which is sensed by containing a predetermined volume of grain between two conductive metal surfaces. This was the principle of working of this moisture sensor. Then calibration is very important for this type of system. So how this calibration can be done? Calibration of yield monitor is done by measuring the yield measured by the developed yield monitor and an electronic scale. So first we have to do the calibration of this system by measuring the yield by the yield monitoring system as well as by the electronic scale. And then grain density is measured manually by using grain weight tester, and cutter bar width of the combine harvester is fed because that is constant. So in our case, this was 4 meter. So 4 meter, we have to feed that data in that system so that he can know that this system can know that what is the cutter bar width, and then how much speed is for traveling. This data is coming from the GPS. And then for the traveling of 1 meter of the combine, so it means 4 meters square. 4 meter is the cutting width. And if combine travels 1 meter ahead or forward, so for the 4 meter square area is harvested. So then one data is generated by that yield monitoring system. So it means each data was coming for the 4 meter square grid. So this then calibration factor. First, this is default value 20 is coming. Then we have to calibrate, and then this calibration factor is reduced slowly. So calibration factor need to be adjusted depending upon normal variation within particular crop, different varieties of crop, and operating characteristics of individual combines. So then this adjusted correction factor is calculated from the relation given below. So this is the relation that adjusted correction factor is equal to F into WA divided by WS. So WA is actual weight of grain measured by that electronic scale, and WS is the grain weight measured by yield sensor. So in that way, this adjustment in the correction factor is given, is calculated, and then it is fed to the system. So then slowly this becomes accurate, the system. So this is finally this formula to calculation or to calculate this yield per unit area. So volume of the grains per unit time, which is the gain product of height of grain and area of lugs, then density of grains, then forward speed of the combine, which is measured by GPS, width we have to feed, moisture content data is also coming. So finally this yield data is coming or calculated by the system by using this formula. There's something more information on how to operate this combine in the field. So final appearance of yield map depends on how the combine is operated. Combine must be operated uniform swath width. So it was 4.2 meter actually, but we given 4 meter because sometimes operator leaves some cutter bar not to be fully in operation or not to be fully utilized. So in that way, we have given only 4 meter to ensure accurate yield data. The width of the header must be manually entered into the monitor. GPS antenna location is also to be manually entered into the monitor. before start harvesting, tier must be set. That tier means that we have to first operate this combine empty, so that there is a number of lugs or every speed or everything is to be get by the system. So this is how you can say operate this combine when this yield monitoring system is fitted. So this is data generated, as you can see that actual area, then calculated by the sensor, then there is error calculated. Similarly, this weight, and then this correction factor, then error in yield method. So this is how this data was generated, and then we finally come to, as you can see in the S9, or you can see from the S5, S6, S7, S8, S9. This correction factor is same, 2 correction factor is there. So that's why this, you can say now error is minimized. So error is only 1%, 2%, or you can say nearly 2%. So this is then was operated for another field. So when there was another field, so there is error has been increased. So it means again we have to calibrate this system for that field. So this is, you can say, this is the process, or this is the methodology for the yield, accurate yield measurement. Then there is also a time lag. Time lag is basically because cutter bar is somewhat in front of that tank where this measuring of the data is done. So that is the time lag that we should also know, that how much is the time lag, so that exact yield maps can be generated by using this yield data. So these are the maps generated, as you can see. That's this long leg is that from where combine has been started, then coming to field, and then area is harvested. So different color means this different value of the yield. So this is also given in some range, as red is 0 to 1000, and then 1000, 2000, 2000, 3000, and this you can say green, and then blue. So 4000 to 5000 and more than 5000. So in that way, this yield maps are generated. And similarly, on the right hand side, this moisture map is also there. So moisture is changing or ranging from about 10 or 14 to 22 plus. So this is the measurement of the moisture. Then these data are transformed as we have time lag, and also this range is given to the software. So they transform this yield map in, because that yield maps are basically in 4 meter square grid. So now we can have some more variation in the data. We can put that values in the software, and then these maps are transformed. So similarly, these are also for the another field for the rice harvesting. And this is another spatial maps are generated in a broader way. So now you can see that if color variation or 3-4 color variation, so you can see that these are the fields as this color is darker, so there is more yield, and there is lesser darker or this you can say weaker portion or weaker color, so that, or lighter color, so that color is giving basically lesser yield. So in that way, these yield maps can also be generated. So similarly for the another field, this yield maps or spatial maps of that yield. So there was also provision to have to look that where this combine is working. So Google Earth view of that harvested field. So this is also there was you can say provision to check that where this combine is working and how much area and this look of that. And then this is we tried now next step is that we have now yield data. So now we have to check that in my field where this yield is lesser. So what are the reasons for that? So actually that is the management. So if we come to know some, we can conclude something that if as in this field, yellow color is lesser yield or below 3000 yield, and where the blue is there, so that is above 4,000 yield. So what are the reasons for that? So then we taken the data of EC of the soil EC data. So now you can see that where this soil EC is lesser as 0.5, 1.5 in this blue color. So yield is also lesser. So where this EC is more, so there is also yield is more. So in that way, we have to calculate or we have to measure another data, and then we can correlate with that data to the yield. So what other data are important along with this yield data? So this is basically there are as soil survey should be there, crop yield. Let us suppose we have measured, then elevation of the field or terrain or topography, then soil electrical conductivity, then soil nitrate, many parameters of these soils, then imagery collected by satellites or by using drones. Then how much was applied and as planted maps, then machine information in terms of fuel use, engine load and RPM, field scouting for the pest and disease. All these stuff of data we have to calculate to manage the farms in precise way or in a better way or in an optimized way. So these are the other data which can be correlated with the yield. So this is how drone or satellites can be used to collect this agronomic data, or you can say that how much fertilizer is to be applied. So this is of that data. Then machine data in terms of what is the speed, engine load, what is the pressure, what is the speed, what is the fuel rate, what is the engine torque. So in that way, this whole machine data is also recorded during the operation of particular operation to be done on the field. So this is, you can say, NDVI image of the field. So this is basically NDVI gives the information about chlorophyll content in the crop, or chlorophyll means that how much urea or how much nitrogen we have to apply in that field. So that NDVI maps are generated. So they give the data that where this fertilizer requirement is more or where this fertilizer requirement is lesser. So this is then this is multi-year data is taken as this 3 years data is taken. Then this final map has been generated. So this you can see that wherever this yellow part that an average but unstable yield, where there is green part there is high stable yield, and there is red part that is low stable yield. So now this conclusion is to be drawn from the multi-year data or temporal data, spatial data, as well as this is basically temporal data. Similarly, for the 5-year-old yield data for the soybean crop with variability. So this is now come to conclusion. CV is given that how much variation in this, as red part is lesser variation, and this greener part is having more variation, or you can say temporal variation in the field. So this is how this multi-year data or temporal data is useful to conclude something. Then this is soil pH mapper we developed in our department or in our university. So this soil pH mapper was used to generate that soil pH maps. So now this different color means different pH. So this is for the 3-4 fields we selected, and then we evaluated the system. So as earlier we were discussing that this data, very important. Data is the mining. So this is called big data. So big data is what is big data? So big data is data that have scale and then diversity and complexity that require new architecture, techniques, algorithms, and analytics to manage it and extract value and hidden knowledge from it. So this is how we can use by the use of these advanced technologies like cloud computing, wireless connectivity, and consumer devices such as smartphones, tablets. So all this is by the use of these technologies, we can generate this big data. And then this data mining. So data mining means usme se information is to be extracted from that data, and that output is given in that understandable format. So there are various data formats like shapefile, TIFF, ARC, IMG, LIDAR, all these different categories data are there. So they can pose issues when working between different platforms or interfaces or software. So there is one world over agency, that is AG Gateway, that is non-profit consortium of businesses serving the agriculture industry. They are basically developing standards for this. So this is ADAPT or AG Data Application Programming Toolkit that is developed by this AG Gateway to establish standard which simplifies data transfer and communication between many different machine brands. So that's all as far as my topic is concerned. So now you are most welcome to raise any question. So I will try to answer that. That's all.
Haji sir, Haji.
So my presentation is over. Now we can discuss, or they can raise their question and I will try to answer.
Chat box में sir, chat box में वो लोग अपने questions लिखेंगे sir.
Okay.
रोहित जी chat box on करिए आप.
Done, sir.
सर कुछ लोगों की क्वेरीज आ रही हैं कि पीपीटी चाहिए, पीपीटी शेयर करेंगे आप कि नहीं?
PPT I have already shared with you. Now
आपने मुझे शेयर किया, मैं ग्रुप में कर दूंगा इन लोगों के.
it's up to you that if you want to share. I don't have any issue in that.
ठीक है, बस आपसे अनुमति लेनी थी जो है.
हाँ नहीं, कोई नहीं, कोई नहीं.
सर प्लीज आप चैट बॉक्स देखें, एक क्वेरी है सर. Please tell what type of drones can be used for live monitoring. Could you recommend few brands?
So where is the question? PPT required, that's okay. Then bucket full presentation, nice presentation, informative presentation, nice presentation. Please tell what type of drones can be used for live monitoring. Could you recommend a few brand or model? Okay. So this question is raised by Harinder Singh Rayat. Okay. So Harinder Singh, I think you are from Punjab side. Anyway, so this your question is that what type of drones can be used for live monitoring. So this is there are 2-3 types of drones like nano, then micro, and then this small, and then medium. So these are used in agriculture purpose, but this for your live monitoring, what you want to record that live monitoring is crop monitoring. What is your target? So if you are talking of crop monitoring, then this micro and nano are okay. But if you are using for spraying as well, so then this small category is used. So but I cannot recommend any brand, or I will not, I can promote any brand or model. But there are many now startups are working in this area. So I think you can visit DGCA website. So on that DGCA website, this is mentioned that what brands or what models are recommended by the DGCA. So only use DGCA recommended these type of drone. So this is only my recommendation. Okay. So
ठीक
then
है डॉक्टर साहब, बाकी मैं पीपीटी आपकी शेयर कर दूंगा, उसमें ईमेल है, ईमेल पे अगर किसी पार्टिसिपेंट की क्वेरी होगा तो वो ईमेल कर लेगा।
right.
ठीक है सर। हाँ ज्योति जी आप बोलिए।
Thank you so much, sir, for such a wonderful presentation. I hope sir have explained very well to all the participants that why there arises a need to shift from normal or conventional practices toward precision agriculture practices. Sir has discussed with us the previous scenario of how we are having the production, what is the water status, what are the nutrient requirements in our country, and what is the present status, and what are the technologies which we would be having and or recommending for increasing the production without disturbing the resource base of the country. So thank you so much, sir, for such a wonderful presentation. And I
madam.
thank you.
Welcome.
I
Okay,
thank you
welcome,
once
madam.
again. I thank you once again, sir, from AgriMeet Foundation and from CSGMU for such a good lecture, and hope to have with you with us for next sessions also. Thank you so much, sir.
Okay, madam. Thank you.
बहुत बहुत धन्यवाद डॉक्टर साहब, नमस्कार।
Okay. Okay, डॉक्टर साहब, कोई बात नहीं जी, वेलकम।
So I thanks all the participants for very cooperative attitude toward the training. So thank you one and all for today's session. You can now leave the session. Thank you one and all.
Okay.